So I gave you back your exams. You saw that I did a pretty big adjustment. I took off 10 points on the multiple choice, which is a huge amount to take out given how many points we had.
You didn't tell me which ones I got wrong.
Oh, absolutely I did. Okay, so here's how to read this. I will take Bryson's. You have, and I will not read what he got right and wrong. Is you read this, it shows test key and it shows you the correct answer on the test key line. Underneath it has answers. If there's a dash, that means you were correct. If it has a letter, that means you answered what it shows instead of the correct. A lot of times people read this and they say, well, for my answer it says D, and I looked and I did put D. Because that's what you put, but it wasn't the right answer. The right answer was the one above it. So that's how to read which ones you got right and which ones you got wrong. And it was very weird. I have the computer just randomize the order of the answers. And there was a stretch of, 8 straight C's or something crazy like that?
Yeah, that sketched me out there.
It throws me off if there are like too many repeating. So I'm like,
it was weird, but I just told the computer to randomize, and that's what it did.
So then the red pen that you used, the red pen that you used to grade.
Well, there's only red writing on Amber's because I was checking the ones that the people missed the most to make sure that the answer in the answer key was indeed the correct answer. Yeah, I used yours to check that.
There's red right.
Oh, that on the back page. Yes. Okay.
No, he circled my question.
Hosanna.
So the language of science, they primarily use Latin.
No, we primarily use math.
Math is not a language.
It is.
Yeah. Wait. See, I think I put Latin. Math is not a language. I was Latin at first, but then I thought good and hard and long about it.
This is something that comes from the textbook. That mathematicians consider physics just applied math, and physicists consider math the language that we speak. Any other questions?
She is not supposed to be sweet like this. Yeah.
I heard her T question, not what her statement, not what you said.
You should ask somebody smart.
So they got to figure out what I want to argue first.
I gotta figure out what I want to argue.
But okay, so in science, educated guess, I thought it was a theory and a hypothesis.
A hypothesis is an educated guess. A theory is a hypothesis that has been tested enough times that you have a fair amount of confidence in. And I mean, that second one is an important thing, understanding what the difference is in a hypothesis and a theory. The first one is, more a question for relating to science and physics. Yes, Amber.
So a stone is thrown vertically upward at the top of its vertical path with acceleration is. Why is it equal to gravity?
Okay, now this is something we went over a few times in class. If I throw a stone up and it's at its highest point, what is it going to do at that moment? Well, let me back up and phrase that better. What is its velocity at its highest point at that instant? Zero, right. At its highest point, it's not moving. And so what is it going to do a split second later, a split second after it's at its highest point? It's going to come down, right? And so that means its velocity is going to be changing in the downward direction.
Ooh, what number was that?
7.
So its velocity is going to be changing in the downward direction. Some people get velocity and acceleration confused and they say 0. But if the acceleration was 0, that its velocity wouldn't be changing. And so it'd just be hovering at the top, not coming back down.
Wait, so what's the answer?
The answer is, through the entire time of free fall, the acceleration is the acceleration of gravity downward, 9.80 meters per second squared downward. Assuming that air resistance is negative.
I'm sorry, I deserve that point. Oh. Oh, yeah.
All right. Well, we are starting today talking about chemistry. So physics, it's going to come back for the final exam, right? A goal of any class is the students learn something. So at the end of the semester, you have that knowledge. So you can't just forget all the physics stuff, but now we have to go to a different fundamental field. Chemistry is studying everything around us. Now, one thing that I want to point out right at the get-go, there is a certain common understanding or belief that chemicals are bad and dangerous. Has anybody heard that?
Yes.
Yes. If you talk to my wife, she thinks chemicals are dangerous. And I've told her enough that now she knows that chemicals doesn't mean what she thought it meant, but she still uses it because she says everybody understands chemicals means this and not that. Chemicals are things made up of atoms. And so water is a chemical. Oxygen is a chemical. Some things are more complicated. Vitamin C is a chemical. Doesn't mean they're bad because they're chemicals. Some chemicals, of course, are bad. You know, arsenic is also arsenic is a chemical. Strychnine is a chemical, right? Some chemicals are bad, but chemical doesn't mean dangerous or bad. Chemical just means that it's something made up of atoms, which is what we're studying here in chemistry. Another thing that is really frustrating is the statement, if you can't read it, you shouldn't be eating it. Talking about things like if you look on the ingredient and it says, you know, acetylsalicylate. You're like, acetylsalicylate, what the heck? I probably shouldn't be eating that. Well, acetylsalicylate is the base for acetylsalicylic acid, which is aspirin. And just because you don't know the name doesn't mean it's dangerous any more than being chemicals means it's dangerous. So I want to make sure I get those out there before we get started with chemistry, just so we don't have misunderstandings there. So talking about the history of chemistry, back 465 BC. Remember, BC, that means before Christ, very literally. And people who don't want to invoke the name of Christ will say BCE for before the Common Era. Common Era meaning the birth of Christ. So 465 years before Christ was born, roughly, Democritus came up with some ideas involving what we now understand to be chemistry. And I'm going to go through these and mark the ones that we still believe to be true, because some of these we still do. One, atoms are indivisible pieces. In fact, the word atom is Greek for indivisible. We now know that's not exactly correct. It's approximately correct, but radioactive decays, what's going on is you're breaking an atom. If you have a nuclear fission bomb, something like Fat Man or Little Boy that were dropped in Japan, those were atoms breaking into smaller pieces. A nuclear power plant is running on atoms breaking into smaller pieces. So now we understand now they're not indivisible. All matter consists of atoms. We still believe that's true. Now, I should specify all matter, all common matter. You can have novel matter that doesn't consist of atoms, but all common matter consists of atoms. Okay, next one. Atoms are indestructible. We still will say something to that effect, but if you can divide them, you know, in the special cases where you can divide them, then you can also destroy them in some manner. Atoms are solid but invisible. Solid, I would have a hard time with. Invisible, certainly I cannot see an atom. It's way, way too small. Atoms are homogeneous. They're the same, spread out evenly. No, not so much. Atoms, different size, shape, mass, position, arrangement. That's definitely true. And then these here, solids are small pointy atoms and liquids are large round atoms. When I was preparing for the slides, I was looking over this and I was like, well, that doesn't make any sense. Oh yeah, that was an old belief, not one that we have today. But we have two things here that are most whoops, that was the wrong one. that are most definitely correct that came from Democritus. And the most important one is actually this one here that's approximately true because Adam means indivisible. With liberty and justice for all. Now we go forward 130 years or so, still long before the birth of Christ, and we have Aristotle. And Aristotle didn't believe in the atomic theory. He didn't believe Democritus, who had said, if I take a block and I break it in half, I'll have 2 smaller blocks. And if I keep breaking the blocks in half, I'll have 2 smaller blocks until I get to the point where I can't split it anymore. That was Democritus' logic for saying there must be some fundamental piece. Aristotle didn't buy into that. But he said that you have these materials, 4 elements that everything on earth is made of. Everything on earth, according to him, was made of earth, water, air, or fire. Remember, I talked about their natural positions. Earth's natural position is down there. Water's natural position is on top of earth. Air's natural position on top of water. Fire's natural position on top of air. So that was the idea that Aristotle had. And because Aristotle was such a great thinker, people pretty much abandoned Democritus and said, that must be it. And so that would have been the understanding of the educated people in the time of Christ. Now we move forward. Notice the time difference. 335 years before Christ to 1880 Anno Domini, which means the year of our Lord, actually. That's why they say in the year of our Lord, this year of God. Year. Okay, so that's based on the year Christ was born, according to reckoning that wasn't quite right. So it's off by around 4 years from actually being currently 2019 years from when Christ was born. So John Dalton explained that chemical reactions used exact ratios of elements. Like if I have this much of this and this much of this and I mix them together, I could get this much of a product. And if I double this one and leave the other one the same, it's not going to change. If I double them both, I'll get double the product. Right? He did experiments like that to show that there's some kind of ratio, exact ratio, between the different chemicals that are used. And so we have this word element. And elements is a material made of only one kind of atom. So if you look at the back of the classroom, you have the periodic table of the elements, the types of atoms. And we're going to learn about that in today's lecture. That's listing all of the elements. I should probably just go to the next slide rather than quoting what's on it. And then, oh, this isn't even the next slides. It's like mini down. I guess I won't go into that now. I thought it was the next slide here. We have 118 elements. This periodic table that's back here is about 4 years old. And because it's 4 years old, elements 113, 115, 117, and 118 have placeholders. If we get a new one, which we should sometime soon, we'll actually have names for them because they do have names. And when I have the periodic table coming up here, you'll see that I have written in what the names are, typed them in, so that we can go from there. So going forward with our understanding, around 1880 was John Dalton. Around 1904 is when things started happening. So J.J. Thomson was studying cathode rays. The old television thing. The old television thing is a cathode ray tube. And what he found was that it was shooting charged particles out. And by careful experimentation, he found those charged particles had a negative charge. What kind of particles have negative charge? Electrons. And so he determined that there were electrons in atoms. And so he said, well, if there's electrons in atoms, then the atom must be this slurry. So this reddish stuff is supposed to be just random positive charge spread around with these little negative spots. And so this was called the plum pudding model, because apparently plum pudding is a smooth slurry with raisins in it. And so the raisins would represent the negative charges, the electrons, and then the pudding would be the positive charge spread everywhere. So 1904, this is after my grandfather and grandmother were born, this was the new discovery. I say that just so we can kind of understand it's fairly recent. 1909, 5 years later, there was a great discovery in Ernest Rutherford's lab. It's called Rutherford's gold foil experiment, but it wasn't done by Rutherford. It was done in his lab. You see the gold foil experiment says by Hans Geiger there. I think I copied that from our textbook. It was actually Marsden who did the experiment, is my understanding. You had the head of the lab, Rutherford. Working for him, you had Hans Geiger, who's kind of famous, right? You've heard of Geiger counter, or Geiger-Mueller counter if you want to be complete. That's the guy. And then they had Marsden, who was the new lab guy. And Geiger goes to Rutherford and says, I think it's about time that we let Marsden do his own experiment. I think he's developed that point. And so Rutherford gives Marsden an experiment to do. And this is the way it kind of works in research labs. When you're in graduate school, you often will have your professor says, here's something that I'd really like to know the answer to. Go do it. And so what he wanted to do was to study what would happen if you shot helium nuclei at gold. If the plum pudding model was correct, then the gold should just be this nebulous positive charge, and then you should have these little electrons. They knew that the helium nuclei were way more massive. By the way, the helium nuclei are called alpha particles here. They knew they were way more massive than electrons. So I figured if I make a really thin film, gold, by the way, is what we call malleable. You can hit it with a mallet, and instead of fracturing, it just squishes. And so you can make very, very thin gold films. That's why they use gold. So he figured that the alpha particle, if it hits an electron, it might slow down just a little. And if it missed, it would just go straight through. When Marsden did the experiment, he saw that most of them went straight through without any kind of deviation or slowing down. But some of them bounced off at crazy, crazy angles. That didn't make sense. Rutherford, as he described it to people, said, imagine that I'll pretend this is toilet paper. I take a piece of toilet paper and I don't hold it in front of me because I'm not an idiot. But I have it stationed in front of a cannon. And I fire the cannonball. The cannonball hits that toilet paper. And it bounces back at the cannon. That's how startled they were with this outcome. They were sure that there would be nothing bouncing back, that it would be going through and slowing down just a very small amount. After all, think about what we've learned about collisions and momentum. That cannonball would have a large amount of momentum, pretty big mass, very high speed. You hit something with a very small mass, like let's just go with a fly. If the cannonball hits a fly, the cannonball doesn't even slow down an appreciable amount. And yet what they found was their cannonball bounced straight back. And so he said, we must not be hitting a fly. We must be hitting a boulder. Right? There must be something that's really massive there. And so he said, this whole plum pudding model has got to be wrong. There must be a central, very massive piece to the gold. And so he called that the nucleus. And then he said, okay, so we've got this nucleus that's a positive charge. He actually did experiments, was able to determine the size of the nucleus and whatnot. So we've got this central part that's very positive, and then the electrons must be orbiting around like planets orbit the sun. Now, notice here we have the funny word circular orbit. At that time, it was already known that planets did not do circular orbits around the sun. But for some reason, we have the word circular orbits there, that he came up with the idea that they're doing circular orbits around the nucleus. So that's what we call the planetary model. So here's a picture showing basically the planetary model. This is actually the Bohr model, but the Bohr model is based on the planetary model. So you have the nucleus in the center that is positively charged. And then you have electrons doing circles around it. Now, very quickly, it was realized this couldn't be right. Niels Bohr, Danish physicist, came over to work with Rutherford. And one of the things they realized right away is that if you have electrons going around a circle, they should be losing energy. And if they lose energy, they'll fall into the center. And so, in fact, according to the planetary model, electrons should all fall into the nucleus in less than a millionth of a second, which means that you would have no atoms with electrons orbiting them. So they knew that there was something wrong. And then there's another cool demonstration I'm going to do. I've got to close the blinds. I've got to see that before class. That illustrates a significant problem with this planetary model. And that is, if you look at the light that comes from atoms that have been excited, that is, you give them energy, you see only specific colors. You don't see the entire spectrum of a rainbow. And so I'm going to do a demonstration here so you can see that effect to understand what it is. So I'm going to give you some glasses here. I do want these back. These are actually made to be children's party glasses, but they're still going to do the trick. They're called diffraction gratings. So you put these babies on, and yes, I do want them back. And first thing to note is, when you look at the lights, you see cool stuff, right? So describe what you see when you look at the lights. Okay, you see rainbows, you see colors. One of the things that I love is if you look at a light that's, off in the distance, you should be able to see like sheets with different colors. So if I look back in the corner, I see a reddish sheet, a yellowish sheet, a greenish sheet, and a violet sheet. You see those?
Yeah, but
Not in that order? That's because these lights are actually making those specific colors. They're not making a complete spectrum of colors. There's only specific colors. But the way we see when those colors are combined, we see it as white. So I'm going to turn off the classroom lights, and including that, turn off the projector. And first I'm going to turn on a little bulb here. Let me get stuff out of the way. And we're going to observe what happens. So, ow, poked myself. So it's a little bit warm. It's giving off light. If you just look at the main part, you'd say that's orange in color, right? But if you look off to the side, you see the colors that it's made of, and you see what we call a continuous spectrum. Starting from the inside out, you see green, yellow, red, correct?
Yeah.
You might be able to see just a slight amount of blue, but not very much. Now I'm going to make it hotter. As I make it hotter, it gets much brighter. In fact, one of the things that we didn't have time to get to in physics, as you double the temperature, the brightness is going to go up proportional temperature to the fourth power. So if you double the temperature, 2 to the fourth is 16. It'll be 16 times brighter, just doubling the temperature. Now you should be able to see a little bit of blue. And you see that's moving more toward a yellowish color. If I keep heating it up, see it's getting much brighter. And now you see the blue coming in nice and strong. So when you heat it up, you get more blue light. So the lights you see and that color that your brain interprets depends on what colors are present. We call this a continuous spectrum because you see all of the colors in the rainbow. There's not individual ones, but all of them. Now we compare that to this. This is either hydrogen or helium. I don't remember which one I left in there at the end because I tested both. Yeah, this is hydrogen. It's not perfect. There's some water that's gotten in there. If it was perfect, you wouldn't have, see all of the little lines between the kind of bluish one and the reddish one? Well, the very bright red one. Those shouldn't be there. Those are because of contaminants that have leaked into the tube. But this is hydrogen gas, and with the hydrogen gas, you see there's certain colors. You have a bluish color, a red color, only specific colors. You don't have all of the colors. And if you change the gas, you change the colors present. So I'm going to change the gas. I do that by simply changing the tube. So this one has helium in it instead of hydrogen in it. And this one here, you can see it hasn't leaked, so you don't have all of the little lines there. They're kind of continuous. You see it's a very different set of colors in the helium gas compared to what you got from the hydrogen gas. So you have distinct colors that come from different gases, which tells us something about the energy of the electrons in the atoms. So the fact that there's only distinct colors here means there's only specific energies, and that was something that was contradictory to the Bohr model, or excuse me, to the planetary model.
Why do we see the lights in like a perfect 90 degrees?
Okay, these are actually, because they're made to be children's party glasses, they have diffraction gratings that are vertical and horizontal. And so that's why. So the planetary model was quickly scrapped. Notice 1909, now 1913. So within 5 years it was scrapped and replaced by the Bohr model. Niels Bohr, like I said, the Danish physicist, came up with a model that was an expansion, if you will, of the planetary model. He kept that the electrons were doing circular orbits, which is why this picture looks the same. But he introduced the idea of stationary states, that you only have certain energy levels that the electrons can have in an atom. Only those certain energy levels then would allow him to explain why we had that spectrum of only certain colors. And so we call this a quantum model. Whoops, I thought I still had it in the highlighter. We call it a quantum model because quantum, I swear I changed it. Quantum means that you have steps rather than continuous values. So a quantum model, you have certain energy levels. As we understand things now, I know that Hosanna has already taken chemistry, so I keep looking at her. We talk about shells that the electrons can fill in an atom. And these shells are given letter abbreviations. So the lowest energy shell is the S, then the next one is a P, then the next one is a D. And you can only have 2 electrons in the S. You can have 6 in the P, 10 in the D, and so on as you go up. We have moved away from the Bohr model to the quantum model. So Bohr's model was a quantum model, but it's not the quantum model. The quantum model makes a big shift from the Bohr model. And that big shift is where the electrons are. In the planetary model, as in the Bohr model, the electrons were doing circular orbits. In our quantum model, we don't know the path an electron takes. We don't even know where the electrons are. But we can calculate where they're likely to be found if you go looking. And so we say that the electrons are filling a shell that has a probability of where you're going to find the electrons. So this thing here, notice it's kind of fuzzy. This indicates it could be anywhere in this region, anywhere in that, and this is an S shell, so it's spherically symmetric. The S does not stand for spherical, it stands for sharp, but it's spherically symmetric, the distribution you could find the electron in. A P Notice we have P here. A P shell looks something like that. You're likely to find the electron somewhere in one of the lobes of that dumbbell shape for a P orbital. And then this here, I believe that's one of the D variations. I didn't look it up to be careful on that. And that you get funny looking shapes that you can look up. So our understanding of the atom has changed quite a bit. And quantum mechanics is what actually gives us these shapes. Nothing you're going to study for this class is going to help you to do that. So we're not going to worry about that. But here's a really important statement. The absorption and emission spectra are explained by electrons moving between these energy levels. So, oh, yeah, I don't have room to write on here. Well, I have a picture coming up after this question that goes with that. So here is a question just to make sure you've been following along as we introduce atoms. First, I should say, why are we introducing atoms? Because chemistry is the physics applied to atoms. Which of the following are incorrect statements about the atom? R implies that more than one is incorrect, but obviously there's going to be probably more than one correct. So let's just go through each one. Atoms have been around since the beginning of the universe. True or false? True. Now, if you want to get all technical Big Bangy on us, at the Big Bang, the energy density was so high that you didn't have atoms. And it wasn't until about 300,000 years after the Big Bang that electrons could merge with nuclei to form neutral atoms. But from that point on, the atoms have been around continuously. And in every breath you take, there is probably at least a handful of atoms that were in the last breath that Christ took when he was on the cross. Because those atoms just keep getting reused. So when you eat food, you're eating atoms that were part of somebody else. It's not cannibalism. The atoms aren't really...
I'm never eating again.
I'm never eating again. Great.
You're never going to breathe again either.
Yeah, never going to breathe, never going to eat. But it's okay. So the atoms are fundamentally perpetual. Not exactly, but fundamentally. Yeah, basically. Atoms, so that's a true statement, basically. Yeah. Within reason. Atoms are mostly empty space. What do you think? True or false? Okay, true. With the planetary model, you have the atoms with electrons doing orbits around. The size is always wrong scale when we draw pictures because the distance from the nucleus to the electron is really big compared to the size of the nucleus. In order to show a nucleus that's not just a dot, we make it so the scale is wrong. But atoms are indeed almost completely empty space. So you're almost completely empty space. When I was a kid and I read this, I was like, I should be able to walk through the wall. I've got to figure this out. How can I walk through the wall? What I didn't understand is, while the atoms are pretty much completely empty space, there's the electrostatic force holding the atoms together. And I can't pull them apart to push an atom between them. So I can't walk through the wall. Yes,
Isn't
Grace?
it true, too, that like when we touch something, it's not actually like touching the atoms? Like,
Right.
So it's like there's like a force that's super repelling or something.
That's correct.
So that's why you can't walk through the wall, right?
Yeah, it's the same. Yeah. So A and B are both true. Atoms are perpetually moving.
Unless it's at absolute zero.
Okay, unless absolute zero, that's also true. In fact, even at absolute zero, quantum mechanics says they can't actually come to rest. So that's a pretty good statement too. I said, which of the following are, probably should have been is, because those first three were all correct. Last one must be incorrect. Atoms are manufactured in plants and in humans during pregnancy. How's a baby made? Not talking about how you get pregnant, but how's the baby develop?
Like the splitting of cells.
Okay, splitting of cells, not atoms. The atoms are incorporated and you make new cells, and then you split them, you make new cells. The atoms aren't being manufactured, the cells are. from atoms. And so really only one of these was incorrect. Whoops. I am on the highlighter mode. Go away, highlighter.
Dr. Webb,
Yes, ma'am.
if I stick a fork in the outlet, it'll just like shock me a little bit, like I will die.
You could.
I could die.
Yes.
Interesting.
So don't do it.
Great. I'll reconsider what I was going to do after this class.
Okay. We should talk.
Let's get the nurse up in here. I was kidding.
Elements. This is where I was going to go a while back, and then I saw, wait, it's a long ways until I have the elements. So, when our textbook was published, there were 150 that had been identified and named. Now there's 118. We say that our periodic table is complete. Periodic tables in the back of the classroom, we'll talk about in a moment. Only 90 of the elements of the periodic table are found in nature. They're naturally occurring. So if you look at the periodic table, on ours, the elements that are in black, you could dig into the earth and find them somewhere. The ones that are, I can't read them because it's white on white, those are ones that are only found when humans make them. They make them by smashing stuff together. So, once again, atoms can be created by smashing stuff together. So we have 118 distinct kinds of atoms, 90 found in nature, and an element, I think we already have this, is a pure material, only one type of atom. So if I have elemental gold, I have only gold atoms. An alloy would be a mixture of metals, and then we have compounds and stuff, words that we'll learn coming up. Now the things that make up an atom, we have in the atom the nucleus, and the nucleus has protons and neutrons in it. Protons have a positive charge. Neutrons have a neutral charge. I don't see the word neutron on there. So it's up here, though. Neutrons are just like protons, but zero charge. Protons are just like neutrons, but a positive charge. Protons and neutrons are about 1,800 times as massive as electrons. So when we talk about the mass of an atom, we ignore electrons. What's 1 or 2 1,800ths of the mass? So we just add up the mass of the protons and the mass of the neutrons, basically. So the nucleus, protons, and neutrons. And then we have electrons that are orbiting about. No one can tell you where. We can only tell you where they're likely to be found. And so we call it the electron cloud, the region where the electron is likely to be found. And most atoms are neutral. Because most atoms are neutral, proton having a positive charge that's 1.602 times 10 to the minus 19 coulombs, and electron having a negative charge that's 1.602 times 10 to the minus 19 coulombs. You have, for a neutral atom, the same number of protons as you have electrons. If you take one away, then it's going to be ionized. All electrons are identical. There's no way of distinguishing one electron from another electron. You can't say, this electron is red, this one is blue, or anything like that. They're exactly identical. And because they have the same charge, they're going to repel other electrons. So if I have two atoms, here's my nucleus. What's the charge of the nucleus? No, the nucleus is not neutral. Positive. So here's one atom with a positive nucleus. Here's another atom with a positive nucleus. But then each one has its electrons that are around here that are negative. And so if I bring these close together, those electrons are going to repel each other unless we have certain special things happen where the electrons get shared. So that's going to be a lead into bonding when we have that. Now, nomenclature for an atom. Atoms have symbols, and so when you look at the periodic table, you see the symbols. So for instance, helium has a symbol of He. So each element, we can tell you what it is by a symbol. But then we also talk about things like the atomic number. The atomic number is the number of protons in the nucleus. If you look at the periodic table back there in the top right-hand corner, it has numbers. H has 1 in the top right-hand corner. He has 2. Li has 3. Be has 4. 1 proton, the number is called the atomic number, and it's the number of protons in the nucleus. So all hydrogen atoms have 1 proton. All helium atoms have 2 protons. So when I'm going to write my symbol, here's the generic way of writing it. You put the symbol, and then in this lower left-hand corner, you put the atomic number, the number of protons. Top left corner, you put the atomic mass. The atomic mass is going to tell you what the total mass is, and we just get that by adding the protons plus the neutrons. Remember, the mass of the electron is so small compared to the mass of the proton or neutron that we just ignore it. And so helium, I'm going to put a 4 here because that is your most common helium. Because the element is defined by how many protons are in the nucleus, it's possible to have a different atomic mass for the same element. You can have helium-3 or you can have helium-4. Do you have a question?
Yeah. The 4 is called what?
The atomic mass. So you can have helium-3, which means you have 3 things in the nucleus. 2 are protons because it's helium. So if you have 2 protons and 3 things, and the nucleus contains only protons and neutrons, how many neutrons would you have in a helium-3?
Sorry, I'm so sorry. Can you repeat? I don't know.
I can. If you have helium-3,
Yeah.
so if I have helium-3, this means you have 2 protons.
Yes.
This means you have 3 protons plus neutrons. So if you have 3 protons plus neutrons and 2 protons, how many neutrons do you have? 1, yes. So helium-3 has 1 neutron in the nucleus. How about a helium-4? How many neutrons would it have in the nucleus? 2, right. We're good at this math.
Yeah.
So both neutrons and protons are called nucleons because you find them in the nucleus. Electrons, not in the nucleus. Isotopes is a word that we use to talk about things like helium-3 and helium-4. Those are 2 different isotopes of the same element. That P in isotope reminds me that isotopes have the same number of protons. You can actually also have a thing called isotones, where you have the same number of neutrons and a different number of protons. Question?
Both protons and neutrons are called
Nucleons. We use on to mean a particle, so nucleon means particle in the nucleus. So what are isotopes? Atoms with the same number of protons but different number of neutrons. All right, and I've already had the atomic mass. We can look up here at the periodic table once again, and if you look at, and I'm going to use helium. I don't know if you guys can see, I can't, so I keep having to walk back here. If I look at helium at the bottom center, it has 4.00260. That is the atomic mass. That's telling you how much mass we have for a helium atom. Now that's not just the number of protons plus the number of neutrons. What we do is we take the total mass of the atom and we call the atomic mass unit. This many kilograms is 1 atomic mass unit. So that means 1 atom of helium has 4.00260, and we actually use the symbol U for atomic mass units. When I was in high school, we used AMU. Now we just use U. We've gotten lazier. 4.00260 U means 4.00260 times 1.661 times 10 to the minus 27 kilograms per atomic mass unit. So we can convert from that number shown there into kilograms. So the mass of an atom here, if I take 4 and multiply it by 1.7 times 10 to the minus 27, I have somewhere in the ballpark of 6 times 10 to the minus 27 kilograms. That's not a measurable mass to you and me. So the mass of an atom is extremely small. Yes? Do you have questions, sir?
So I see where you get the 4.00260.
Yes.
I see that. And with the fact that you converted it to that, was that just like quick math in your head? Like we would have to actually like.
This is how you convert units. We have 1.661 times 10 to the minus 27 kilograms is equal to 1 atomic mass unit, to 1 U.
Okay.
And so I just have my conversion factor of this number of kilograms per atomic mass unit. So I'm just converting it into kilograms. We like to use the atomic mass unit because it's a nice number to work with instead of 10 to the minus 27 to work with.
Yeah.
All right. The atomic number. I think I'm going to end with this question. What is the atomic, darn it. What is the atomic number?
The total mass of the atom, all of them, so both of these.
It's not. Atomic mass is the total mass. Atomic
Oh, the atomic number, I'm sorry.
is the protons, right. So it's the protons in the nucleus. Let me leave you with one assurance. You do not have to memorize that table. You will be given that table on the test. You need to know what things in it mean, how to interpret it, but you don't have to memorize it. So on Wednesday, we'll learn more about that periodic table. Amber.
Can you go back to the isotopy slide?
This one?
No.
Do you want the test set?
No. I have them all scanned, and I'll upload them to Middle.
You don't have homework this week, right?
That's right. You sent me an email. I didn't respond.
You
Yeah.
guys don't have homework this week?
No, we don't.
I wanted to make sure because, I checked Moodle and I checked the syllabus, but I was like, some teachers are sketchy and like to say that, and then we get homework.
Are we going to be moving on to the next chapter when it's class period?
Yes, that's what the syllabus.
Because this was syllabus, so it wouldn't be like, we're going to be doing properties of the periodic table.
Yeah, we're going to be doing projects of periodic table.
So, do you read the next chapter?
Is that what the next chapter is?
No, because well, I don't know, maybe it is
I
too,
know.
but I just know the the chapter from today talked about period.
Here's what we'll be talking about.
Yeah,
That's true. Because my problem with I tried to learn.
Okay, so we already looked at this,
Yeah,
and this here is we've already talked about that. It goes with it.
You have this diagram. Okay, that goes there. Oh wait, is it in front of it?
Yeah. This is the last slide.
So basically, that's all we're talking about then.
We probably won't get any further.
Okay.
I won't say for sure. I will have slides that would take me further, but we probably won't get any further.
Okay.